the young Earth. And you notice in this drawing, in the sequence, the rotation axis gets tilted, and that will come back into play later on. Okay, so there is a common belief that the moon orbits the Earth. I'm sure you've all heard that. Well, in fact, it does not. The moon, I'm sorry?
Oh my goodness. Yeah.
I hear some voices very quietly. I'm not sure if I'll carry on, but stop me if questions arise. The moon does not orbit the Earth. The moon and the Earth orbit a common center of mass, technically called the barycenter, which is about 1,017 miles, if memory serves, under the Earth's surface. And when one learns in school that the Earth has an elliptical orbit around the sun, well, in real life, it is that common center of mass, the barycenter, that has an elliptical orbit. The Earth and the moon both have wobbly orbits, wobble, 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 as they orbit each other, and of course, at the same time, are orbiting the sun. In this drawing, which is obviously a sequence of taking a wrench, putting it on a smooth surface, spinning it and giving it a push, there is a center of mass of that wrench, and that center of mass moves in a straight line. That is analogous to the elliptical path that the Earth makes. So let me show you another picture of that. In this picture from left to right, you can see the Earth and the moon with the barycenter making the nice elliptical path, and the two other bodies, the Earth and the moon, that is, waltzing around each other. And it's like two dancers on a dance room floor, who are holding each other as they twirl around. The more massive of the two twirls less, and the lighter of the two twirls around more. And so this is conceptually what the Earth and moon are doing in real life. Okay, so let's now turn to the concept of tides. And correct me if I'm wrong, but I expect that you've been told that the moon causes the tides, or maybe you've been told the moon and the sun cause the tides. And that isn't even correct. So let me show you how the tides really occur, because this is highly relevant to the evolution of the Earth, namely the tides. All right, so in this picture on the left, the moon's gravitational force pulls the water on the left half of the Earth towards it. And I made this drawing on the right to show you how the tide, high tide, on the left-hand side bulges out. And as I said, that is indeed caused by the gravity of the moon pulling the water towards it. However, and the sun does the same thing, but let's just stay focused on the moon for now. However, the high tide on the opposite side of the Earth from the sun is not caused by, it's often explained, and I quote, the high tide on the opposite side of the Earth from the sun is water that is left behind as the moon pulls the body of the Earth towards it more than it pulls the water. Well, that's not right. The high tide on the side of the Earth opposite the moon is caused by this the waltzing motion of the Earth. Now, if you imagine, for example, just imagine a ball hanging from a string, and you hold the ball, the string that is, and as you turn around, the ball is going to move out. Well, that energy that you give the ball to cause it to move upwards, move outwards, away from you, is analogous to the energy that the moon gives to the Earth, causing the Earth to be orbiting around the barycenter, and the water on the side of the Earth opposite the moon is being pushed away, being pushed away from the moon's direction by the motion of the Earth, not by the moon pulling different distances of different parts of the Earth by different amounts. So the high tide closest to the moon is indeed being created by the the gravity of the moon pulling the water on this side towards it. But the high tide on the other side is caused by the Earth orbiting around its barycenter and causing the water on the other side to be pushed away from the moon. So that's the basic mechanism by which the tides form. Two different reasons for the two high tides of the Earth. And if you're interested in seeing more details of that, I highly recommend the website, the NOAA website, Our Restless Tides. It does a really, really good job of explaining what I've just said in more detail, with also some equations and so on. But just a suggestion. Okay, now what I did not include in what I just talked about before is the fact that the Earth is spinning. So let's put the rotation of the Earth back into the storyline. All right, now let me invite you to look at the right-hand side, just for simplicity here. The spinning of the Earth spins once a day, of course, is so fast compared to the moon's orbit once a month, more or less, around the Earth. The spinning of the Earth is so fast that the high tides created by these two mechanisms I just described are not in a straight line between the Earth and the moon. In other words, if the Earth was not spinning or the moon was not orbiting, the high tide would not be here. It would be there in a straight line between the two bodies. That is not the case. What is happening is that the high tide is about 10 degrees ahead of the moon as the moon is orbiting. The Earth's rotation and the moon's orbit are both counterclockwise, as seen from above the northern hemisphere of the Earth. And the so what about the high tide being here up 10 degrees? Can you see the cursor I'm moving around? You can see that? Good. Okay. So the high tide being here rather than there means that the water in this line is the highest, and therefore the force of gravity, all matter has gravity, as you all know, the force of gravity from the high tide closest to the moon is not pulling the moon directly towards the center of the Earth. Instead, the high tide here is pulling the moon, of course, in large measure towards the center, but also it is pulling the moon this way. Let me show you, I have another drawing here. Same thing conceptually. The red line is the force of gravity between the Earth and the moon. The yellow line is the force of gravity from the high tide closest to the moon. And the fact that the yellow line, the force, if you will, from the high tide is not in a straight line means that the high tide closest to the Earth, closest to the moon, excuse me, is pulling the moon forward in its orbit. That's the little red line here. By pulling the moon forward, like the ball on the string I was describing before, the moon is gaining energy from the gravitational pull of the high tide closest to it. The one farthest away, you may well be wondering, what effect does that have? It does have an effect, but not as strong because it's farther away than the high tide closer to the moon. And the closer two objects are, the stronger the force of gravity between them. So anyways, the high tide closest to the moon is pulling the moon this way, and therefore, in part, is pulling it forward in its orbit. It is giving the moon more energy. And as a result of getting that energy, like the ball on the string spinning around, the moon is spiraling away from the Earth. And it's when people hear that, they say, well, if it's spiraling away from the Earth, is it moving faster and faster because it's getting energy? And the answer to that question is no. The moon is spiraling away from the Earth because it's getting energy from this high tide here. But as it orbits farther and farther away, it is orbiting more and more slowly all the time. And to confirm what I just said, not because I said it, but it's been known for a long time, to confirm that, the astronauts on the moon put down, well, you can see these, all the stuff they put down here, but this one right here, called the corner reflectors, is what I want to draw your attention to. The corner reflectors are analogous to the reflectors, the red and orange reflectors on your car. And the way they work is that the light coming from anywhere strikes one, think of the corner of a room, three sides up there. The light coming into a corner reflector strikes one of the three sides. They're polished to reflect the light. So the light bounces off of one side, it hits a second side, it reflects off of the second side, it hits the third side, and these things are designed so that after striking the third side, the light goes back in the same direction from which it came. That's why when you're driving on the road and you have your lights on at night and you see a car, maybe it's not even running at all, but you see the red corner reflectors and the orange corner reflectors, depending on which angle you're looking at it, you see the car because it has the same corner reflectors as they put on the moon. Conceptually, of course, these cost millions of dollars, and the ones in your car you can get for a couple of bucks, but never mind. So they put these corner reflectors on the moon, and they aimed at this more or less in the direction of the Earth. Doesn't have to be exactly, but more or less in the direction of the Earth. And because the moon is rotating, spinning on its axis at the same rate that it orbits the Earth, the same side of the moon always faces the Earth. And therefore, these corner reflectors are always facing the Earth. So what they have done to test this concept of the moon spiraling away is they sent laser beams, and they still do this. They send laser beams to the moon, and these laser beams strike the corner reflectors, reflect, come back, and what they do is they time the round trip. light travels at a finite speed. We know how fast it travels. And if you do this experiment, sending pulses of light to the moon, measuring the round trip, and you do it next week and the week after and the week and so on, you will find that every single time it takes longer to make the round trip. It takes longer because the moon is farther away, and therefore the light has farther to travel to reflect off of the moon and then come back. I just a quick aside here is Buzz Aldrin. I was at a New Year's party with a friend, another astronaut, and his phone rang. He buzzed, his cell phone, and he opened it up, and there it said, "Happy New Year, Buzz Aldrin." So that was kind of neat. Okay, so the moon is spiraling away from the Earth. That raises the question, well, I'll give you some numbers. Today, the moon is moving away about 1.5 inches a year. Okay, so it's a very measurable distance, given our technology and the speed of light. The Earth's rotation. Well, let me preface this point by saying the moon is getting energy from the Earth. The Earth, therefore, must be losing energy. And the way the Earth is losing energy is it's slowing down. And the reason it's slowing down is because the waters of the high tide are continually trying to slide towards the direction of the moon. And they can't because the nasty continents get in the way and stuff. So the waters of the oceans are continually pushing against the land in the opposite direction from which the Earth is rotating. And that interaction between the water and the land is causing the Earth to slow its rotation. And as you can see by the note I made, it's about almost 0.002 of a second per century. Therefore, of course, back in earlier days, the Earth was rotating faster. Then comes the question, well, if the moon is spiraling away from the Earth, is it going to leave orbit? And the answer is no, it will not. And the reason it won't is because as the moon spirals away and the Earth's rotation rate slows down, eventually it's going to get to a point where the Earth is rotating so slowly that the Earth will rotate at the same rate that the moon, farther away now, the moon is orbiting around the barycenter with the Earth. And from then on, the same side of the Earth will always face the moon. The moon will have high tides on the Earth directly pointed towards the moon and away on the opposite side, of course. And from then on, there will not be this leading high tide to pull the moon around because the two bodies will be orbiting with one side of each facing the other forever after. However, that's going to take place so far in the future that the sun is going to blow up a long time before that happens. So be that as it may. All right. This rotation that I just described, the Earth's rotation, will be called synchronous rotation. That's the same thing that the moon is doing today. It's rotating at the same rate that it's revolving around the barycenter. And so this concept will apply, and it does in other worlds, by the way, other planets affected by the sun more strongly than we are, for example, the rotation rate is strongly affected. The sun causes 1/3 of our tides today, by the way. Okay, so from then on, the high tide on Earth will be in a straight line with the moon, and that's that. All right. So having provided that backstory, so to speak, of the moon's interaction with the Earth, the question is, so what? So let's think about what the moon has actually done for us over this length of time. Well, and please correct me if I'm wrong, but it appeared from what I could see on the web that the high tides in San Diego, the spring tides are the highest tides. That's when the moon and sun are either in a straight line on the same side of the earth with each other or on the opposite sides of the earth. The high tides are highest in those two situations. And it's called spring tides. The tide springs up. And the highest high tides that I was able to see for San Diego, roughly speaking, 6 feet high. And feel free to correct me if I'm wrong about that number. Well, it turns out we do not know how close the moon was when it first formed, but it was at least 10 times closer and possibly 20 times closer than it is today. Okay. And that's based on this collision theory of explaining how the moon came into existence. And so I'll take the lesser case where it's when it formed, it was 10 times closer. Given that, it turns out that the tides created when by the moon when it first formed were 1,000 times higher than they are today. So when the moon first formed and the oceans first formed on Earth, the tides were in San Diego were about 6,000 feet high. And furthermore, the Earth was spinning faster, as I mentioned earlier. And we don't know for sure how fast it was spinning. People are still working on that. But roughly speaking, it was spinning about 8 hours a day. The day was 8 hours long. And it has been slowing down ever since then because of the tide effect that I've described to you. So the Earth is slowing down, the moon is spiraling away. Okay. Those 6,000 feet tides, they would have occurred 3 times as often, by the way, as tides do today, because the 24-hour day rather than an 8-hour day. Those 6,000 feet tides, imagine that water going inland for 4 hours, coming back out 4 hours of 6,000 mile high tides. In Maine, it's twice that number, by the way. Scouring the Earth's surface, so that water going over the land and going back out again so quickly and so powerfully because the water is so high, the tides are so high, that water put into the oceans the minerals necessary to create the primordial soup from which life was formed. So the profoundly high tides were a essential factor in enabling life to form in the oceans as early as it did, as quickly as it did. Okay. So this is what I was just saying. There were for an 8-hour day, there were 2 high tides in an 8-hour period. And this is a major factor in life being here as quickly as it formed, as quickly as it did. It's just a nice picture of a tide, well, a wave in that case, of course. All right, so what else has the moon done? That early picture I showed of the impact tilted the Earth's rotation axis. And that tilt to the Earth's rotation axis is why we have the seasons. So let me show you that very briefly. So here's a picture on the top showing the Earth orbiting around with a tilt. It's about 23.5 degrees from the rotation axis being perpendicular to the orbital plane. Okay. And the so what about that is that as a result of that tilt, the sun rises, as you all know, and sets at different places in different times of the year. When the northern hemisphere on the right-hand side here is tilted towards the sun rises the highest of any time of the year on this bottom left picture here, okay, and is up longest. So the energy from the sun is more concentrated than, for example, in March, when the sun is lower in our sky, and the same energy from the sun is more spread out. In winter, when the North Pole is pointing away from the sun is up least, and that same amount of energy is spread out over a much larger area, which is a major reason why the winter is cold, and then down here, the summer is warm. So that's a big deal. Another thing that has recently been discovered is that a rotating planet that does not have a moon like our moon, say the Earth without the moon at all, the axis of rotation, north-south pole, is unstable, which means that, and this can happen randomly, and it can happen quickly, and it can have profound effects, that rotation axis can go from straight up and down perpendicular to the Earth's rotation axis to almost parallel to it, in which case the seasons are so profoundly different that essentially it would have been impossible for life as we know it to evolve on that world, because the cycle of seasons would have been chaotic. It would have been a real challenge. Another thing that the moon has done is that it has slowed the Earth's rotation down from an 8-hour day to a 24-hour day. And as a result, because it's spinning more slowly, the weather is more moderate than it was back in the day when things were going much more quickly. It allows biological clocks, as you probably all know, most animals have built into them a clock. We call it a biological clock, which is based on 24-hour cycle, day-night cycle. And that's why having light in the morning is useful to help reset the clock, because our clocks do not always sync by themselves as they should. But the biological clock of 24 hours is based on the 24-hour day. And if the day had remained 8 hours long, imagine what a day would be like. You know, trying to get so much done in 1/3 the time, it would have been a completely different biological evolution for not only humans, but for virtually all other animals. So biological clocks syncing to a tolerable, quote unquote, 24-hour day is a result of the moon being there. Furthermore, as you probably know also, when it's up at night, it provides light for some animal navigation. And without that, those animals would never have come into existence. It's also, strictly from a technological point of view, it was a challenge to get to the moon, but relatively early in the history of technology, we did it. We did it because it was relatively close. Its mass is relatively low. It lacks an atmosphere, which makes things harder to move into because the air creates friction. If we had never had a moon, then the closest thing that we would have had to go to was Mars. And that is a much, much, much harder challenge. because number one, its distance is greater, its mass is greater, it has an atmosphere, and getting a rocket onto the surface, which is not trivial, by the way, but is one thing, but getting it back off again is still something that we haven't quite figured out how to do. So going into space for human travel to other worlds, the moon was a wonderful thing. And perhaps most important, of course, is romance. The moon is something that it inspires romance in many people. Okay, so that is what we have because we have a moon. And now, what if the moon had never existed? Well, hopefully these things are now quote unquote obvious because we went over them, but the day would be much shorter. I might add parenthetically that the tides created by the sun, which are 1/3 of the tides today, would have slowed the Earth's rotation, but not nearly as much as the incredibly strong gravitational force from the moon when it was much closer to us. So in other words, the tides from the sun, if we had never had a moon, would be 1/3 as high as they are today and would have been that high throughout history. So that's why I say 8 to 10 hours. There would be, of course, very different weather patterns. The heating and cooling cycle, day-night cycle, would be vastly different than it is today. The seasons, remember that the tilt of the Earth was created by the impact. An interesting side point to that tilt in the impact as a result of the impact is that the moon, it turns out, computer simulations show, stabilizes the tilt of the Earth's axis. Not perfectly. The tilt of the Earth's axis does change, but not so profoundly that it would cause a chaotic difference in the seasons from one decade to the next. So it stabilized the seasons, and without the moon, we would have different seasons, sometimes no seasons at all, when the rotation axis is perpendicular to the plane of our orbit. And sometimes there would be months at a time where one side would see the sun 24/7, so to speak, and the other side would not see it at all until the Earth that's when the Earth is tilted considerably compared to what it is today. And I've written stories about that as well, but that would make profoundly different seasons than we have. Another major consequence of the moon was that primordial soup that it created, scouring such a huge amount of land into the oceans, providing the carbon and other elements that are necessary for life. Well, the only way that would have happened in a big way, well, two ways it would have happened without the moon is river runoff, and that's fine, but nothing compared to what happened back in the day. And the other source is from lava flows underneath the oceans, filling up, putting debris into the bottom of the ocean, which is still happening today, by the way. So without the incredible addition contributed by the high tides, life would have been probably delayed by tens or hundreds of millions of years, maybe even more. And so the evolution of life, as I just said, would have been profoundly different than it is today, and it is virtually certain that we would not yet be here. The biological clocks that all of those creatures would have on the world without the moon would be synced to the, let's say, 8-hour day for conversation. So that cycle would have just had a profound impact on virtually every aspect of life for every creature and plant on the planet. Oops. And that is the end of my story. So I will stop there, and I'd be more than happy to answer any questions.
Sorry, I was wondering if you have a question, you could just mute yourself. But we did get a question in the chat. So yeah, they said yeah. Is it correct to assume that the quantity of water from one day was 8 hours long to today is not changed significantly?
The quantity of water, you mean the ocean, the amount of water in the oceans?
I think so, yeah.
It would be different, but not significantly. And it would be primarily different because the different heating and cooling cycles that those two worlds would have would cause different amounts of water to evaporate, to form rivers and feed the water back into the oceans. The impacting body that created the moon would have almost certainly had a profound impact on whatever water we had then. But that leads to the question of when did the water come? And that's still a work in progress as well. So the answer is, yeah, it would have made a difference. And how much of a difference is really going to depend on when the water came, number one, and the effects of the changing day-night cycle, number two. Does that answer the question?
Yeah, I think so. And yeah, actually, there's another question that popped up. If some asteroid wipes the water on Earth suddenly, what happens to the moon?
So if an asteroid struck the oceans and splashed a lot of water into space, is that?
Yeah.
Okay, no, that's a great question. I've never been asked that one before. The short answer is, that asteroid would cause tremendous amounts of damage and, would have been just chaotic. But focusing on the water, if a significant amount of water was launched into space, then yes, the tides would be different, and the evolution of the Earth would be different than it's going to be. So the amount of water on the Earth absolutely has a major impact in the evolution of the Earth.
Got it. And how long after the impact would have the Earth cooled enough for liquid water to exist?
Oh, that's a great question. To the best of my knowledge, it would have had to have been tens of millions to 100 million years. I honestly don't know if the geologists, because that's their realm, have actually pinpointed a number for that.
Okay. And is there a possibility of learning about the KT event from ejected deposits on the moon?
The KT event. Remind me what the KT event is. I don't know.
I think the asteroid that hit the Earth 65 million or so years ago.
Oh,
I'm sorry if it
yeah,
wasn't KT.
Okay, yes, thank you. I think I've heard it in that form, but I didn't. I'm not too familiar with that terminology. So is there a possibility of learning more about the KT from the ejected deposits? Oh, that's an interesting question. It turns out that when there's a powerful impact on a body, planet, on a moon, some debris is splashed into space. And it is very, very likely that some of the Earth debris was splashed into space, and it is very, very likely that some of it struck the moon. So that's the long answer, long way of saying yes. That's a very, and I think that the geologists or lunar geologists are keeping that in mind for studying some of the regions of the moon to see if those regions which have impacts on them were caused by some of that debris 65 million years ago. All right, when would synchronous rotation between the Earth and Moon go out of sync? In other words, if I understand correctly, once the Earth and Moon are, let me say it this way, when the Earth is rotating at the same rate that the Moon is orbiting us, that's synchronous rotation for the Earth and the Moon. And the question is, when would that go out of sync? And the short answer is it would not. Ignoring the fact that the sun is going to blow up long before then, if this were to happen in the life of our solar system, once those the Earth and Moon had that relationship, the same side of the Earth always facing the Moon, then there would no longer be tides, and the Moon would no longer move away from the Earth. And unless a third body came into play, like an impact on the Moon, maybe of something big, unless a third body came into play, they would be locked that way forever. There was also, was there time when the Moon was being formed that it was out of sync, and Moon and the Earth could see? Oh, great question. And the Earth could see the other side of the Moon. And the answer is definitely yes. In other words, it took some time, not particularly long, because the Moon was molten when it formed. But it took some time for the rotating Moon, and we don't know how fast it was originally rotating, to change its rotation rate and become synchronous. But as I said, because the Moon was originally very molten rock, the tides on the Moon were actually tides of rock, not tides of water. And the friction created by those tides of rock changed the Moon's rotation rate from whatever it was, and before then we could see both sides, from whatever it was to what we have today, where we only see one side. So yes, the answer is before then we could definitely, in principle, see all sides of the Moon. And see, Gary says, it seems to me if we had no Moon, the climate might be different, but that would be normal for them. Yes, just as our current climate is normal for us. And I totally agree with you. In other words, the climate, the contribution of the climate to the evolution of life here on our Earth, in other words, the necessity for animals to cope with profoundly different temperature changes and so on, like that. The world, if it had never had a Moon, would have different seasons, would have different temperature ranges, and would definitely require the life forms on it to adapt to that situation. But once they did, it would be normal for them, and then they would be able to live with an 8-hour day and the weather related to it, just as we can deal with a 24-hour day. So I hope that addresses some of your question, Gary. Okay, Marianne, NASA Ames Museum has a meteorite from Vesta when it was smacked and and lost its round minor planet shape. Yep. There are also several from Mars. And in fact, I have a tiny meteorite, or piece of a meteorite from Mars. So it is highly likely that there are some Earth ejecta on the moon. Totally agree with you. Completely agree. Completely. Do the physics allow the possibility of multiple moons forming from the impact? Very intriguing question. The short answer is yes, the long answer is no. And the way that works is that in the time scale that the debris splashed into orbit clumped together, it is entirely possible that it could have had a range of orbital distances from the Earth, so that different clumps would have condensed to form different moons. That's conceptually not out of the question. However, having said that, the tides created by the moons on the Earth, the two moons, let's stay with two moons. The moon closer to the Earth would create higher tides than the moon farther away, and therefore the moon closer to the Earth would be pulled more because it's closer and it is the direct cause of the tides. The closer moon would be pulled more in the way I showed earlier in this talk, would be pulled more forward than the moon farther away, which feels less gravitational force from the Earth and from the tides. So the moon closer to the Earth, creating the higher tides and having those tides synchronized with that moon's orbit, that moon, the closer moon, would be given more energy than the farther moon. And therefore, the closer moon would spiral outward faster than the farther moon would spiral out. And as a result, and it really depends on the masses of the moons and their distances, but as a result, two big moons, say similar to ours, orbiting an Earth-like planet, is very likely that they would eventually collide and form a single moon. So I hope that addresses that question. If dealing with smaller moons, of course, that changes everything, because then the tides are not as strong from the smaller moons. So what I just said before deals specifically with massive moons like our moon times 2. What was the way to get a PhD in physics without full-time? I honestly don't know. I don't know if there is a way to get without full-time enrollment. It is possible that if you were to go to some university and talk to somebody in the physics department and convince them that you are very, very capable of doing physics. Maybe you did it in high school, or as an undergraduate. You're very capable of doing the physics, but you can't do it 24/7. That they may make an accommodation if you can convince them that your abilities in the realm of physics you're interested in are so good that you would make a contribution to science, then it is possible that they would make accommodations. But I think you would have to make the case to them first that it would be worth their effort to work with you on that. Do we know how other moons form around planets after a collision versus something like capturing asteroids and comets? How other moons form around planets? I'm sorry, I'm not sure I quite understand. If you're asking, are any of the other moons in our solar system the result of a collision like ours? The short answer is no. they were either all captured or formed from other debris. So I don't, no, I'm just reading the question again.
Sorry, I was just asking how often this happens. Like, does it happen maybe in other solar systems, or have we ever seen anything else like that?
That's an excellent question. And there are astronomers doing that very research to see whether or not any of the exoplanets that, especially the exoplanets, those are planets orbiting other stars, that exist in the what's called the Goldilocks zone, where water can be liquid and therefore life could form, also have moons like ours. I'm not aware that they have found any yet, but I'm not really up on that, you know, the latest news in that regard. But conceptually, that question, are there moons, massive moons, orbiting other planets and other star systems, is really, really important, and in part because many astronomers, geologists think that it would be hard for life to form without the moon. So finding exoplanet with the moon, that's one of the major goals. Hope I've answered your question, Baron.
Yeah, thank you.
One last thing that the moon has done for us, hours of observational, you're so right, observational delights. I couldn't agree with you more. It's a real treat. And you know, and looking at it in different phases and therefore seeing different parts in detail on the boundary between light and dark is always very intriguing, because it's different at every phase of the moon's cycle. What is the type of evidence that points to the moon being formed from collision debris rather than having formed separately? It's very hard to mathematically / computationally create a scenario with a massive planet like ours and a moon that formed from the same region of interest of orbiting gas and dust orbiting the sun. In other words, the process of creating planets and creating moons makes it very hard for the two to form at the same time. As I'm sure you know, all of these bigger bodies are caused by collisions that where smaller bodies collide with others to make asteroids, say, and the asteroids collide together to make, you know, planets, small planets, and then they attract other things onto them. But the system is so chaotic, the number of collisions involved and the energy of the impacts involved is so great that it would be very difficult for the two objects, Earth and Moon, to form at the same time, you know, together without having had something to cause the moon to be there, other than just the multiple impacts. So that's basically, basically the short answer is, to the best of my knowledge, it wouldn't be possible because of the chaos involved in creating the planets and, of course, the moons. Here's another message. I heard that the moon has a lopsided crust, different on one side than the other. And this was probably due to a larger moon and a smaller moon, which underwent a slow merger early on. Is that true? I've not heard that explanation. The explanation that I've heard is that when the moon formed, after the moon started to solidify its outer layers, there was another big impact. And that big impact created essentially a gigantic crater on the Earth side of the moon. And then magma from inside seeped out, became lava, filling that crater region with the rock, with the magma. And when that lava solidified, it was long after the impacting chaos of the early life of the moon. And therefore, the side that we see, which has relatively few craters on it, that surface was formed afterwards, after the side facing away from the Earth, because of that big impact and the filling of that crater or multiple craters with lava that smoothed out. And yes, those the Maria, that's what they're called, do have some cratering in them, but not nearly as much, because it's much younger surface than the surface on the far side of the moon. I hope that answers your question, Gary. Okay, any other questions?
Yeah.
Well, I can ask one. I'm just curious, given your, background, I'm sure you probably remember the Apollo missions, and there must have been a lot of excitement. Just curious, what are your feelings about the pace at which research has been done since that, just gigantic outlay of funds in the 60s and probably early 70s? My own feeling as a layperson is that perhaps more robotic, automated sorts of, whatever missions could have been done later as well. And with the advancements in electronics and whatnot, we might have gathered more useful data. So, kind of an open-ended question. Thanks.
It is indeed. And as you know, I'm sure, we have sent those robot rovers to Mars. And so we are collecting data there, analogous to the kind of data that you're suggesting we could collect on the moon. And the truth is, we could have. I don't know the history of the exploration periods. In other words, whether or not they decided the moon isn't worth the effort, let's go to Mars, because we can go back to the moon and scoop up the stuff with our own hands, which is going to be happening in the not too distant future. So yeah, it certainly would have been instructive to send the robots to the moon, but sending them to Mars was a bigger challenge and potentially has more opportunity for providing us information, such as, are there any indications of life on the moon? Or are there, different stages of layering from oceans that existed on the northern hemisphere that could have had an effect on both the evolution of Mars and potentially the evolution of life there. So I think that's the kind of reason that we invested the effort in Mars rather than the moon. Am I addressing your question, Sam?
Yeah, I mean, it just seems to me that it wouldn't necessarily be very expensive to have continued something on the moon as well. Just my 2 cents.
No, fair enough. I take your point. It probably was a question of, who wanted to invest the money in that when other opportunities were created, like going to Mars. And at the same time, there were other challenges that were not technology. They might have been political, and I think it's a very complicated issue. But it's an interesting question. And let's see, there were plans to make the Apollo lunar rovers remote controlled. And actually, I think it was the Chinese, correct me if I'm wrong, have sent a mission to the moon recently. I don't know how successful it wasn't following that. But I think that over the decades since we did go to the moon, very little has been done there. And so I take your point, Sam, that it would have been interesting to continue doing that. Ross says there were plans to make the Apollo lunar rovers remote controlled and continue exploration after the astronauts left, but there wasn't time to build in that capability. That's interesting. I honestly did not know that was part of the plan, but conceptually, I mean, from an engineering point of view, it certainly could have been. Very interesting, Ross. All right.
I was
Yeah.
just reading an article on the Apollo 17 mission, the last to go to the moon.
Mhm.
And Harrison Schmitt was the only astronaut up until that time who wasn't a test pilot. He was a geologist, scientist. And they pulled him. He was going to go 2 missions later, but then those missions got axed because of budget concerns. So they put him on Apollo 17. And so he was able to do a lot of really important geological finds when they went on their 3 walkabouts.
And they had a
their
rover too.
EVAs. Yeah, they had a rover and they drove around.
Right.
And the interesting thing is, he said that going to the moon or going to Mars, a person rather than a machine will do so much more, so much quickly to hone down to what they want to find and how they find it and how they bring it back. So, but unfortunately, he was the only one and the last one to do that.
Very interesting history. Well, thank you for sharing that. I do think that it is the time to go back, and I do hope that some of the people who go are not just billionaires, but scientists who can provide those kinds of real-time insights and searching procedures, and that will give us more knowledge, more understanding of the moon than we have today. Of course, they had to bring a car. Can't argue that. There's a moon buggy, analogous to a dune buggy.
Yeah, and are there any more questions?
How can we use crowdfunding? Huh. I don't know if crowdfunding can get to the kind of budgets necessary to go to the moon, but an interesting thought might be to crowdfund some technological devices to take to the moon. So if somebody came up with an idea, made a good case for it, maybe that could be crowdfunded. So that's the direction I would suggest going in that regard. Making the science the thing that gets people interested in financially supporting the effort. Interesting. I don't know. Open source project. And now that we're finding water on the moon, by the way, it's going to make going back there more potentially economically viable, because that water can be made into rocket fuel, and so we could actually blast off from Mars moon orbit, let's say, with fuel provided from the moon to go to Mars and other places. So that's something that's I think in the books. Planetary Society uses crowdfunding, and some CubeSats have been crowdfunded. Okay, very good. I did not know that. Perhaps we can get money from the billionaires and then send them to the moon. There you go. Alrighty.
Yeah, if there are no more questions, I think we can begin to wrap it up. I just want to say thank you to our speaker for coming to speak with us today.
It was my pleasure. Thank you very much for being there. Very kind. And I hope you all have a great rest of your day, and
Yep, thank you
and be
everyone for
well.
attending too.
Nice. Good night.